Greetings everyone, my name is Erlangga Saputra, the presenter of this presentation. This presentation contains several sections. There are
From the beginning, let's get to know this figure. This is an example of catamaran with bulbous bows. Catamaran is a ship with twin hulls, while bulbous bow is a protruding bulb at the ship's bow below the waterline. The increase in commercial multi-hulls, especially catamarans, is a concern in marine transportation related to safety and speed factors. The development of a catamaran hull based on the design criteria provides advantages over monohulls, offering less drag, better stability, and more expensive deck. Catamaran design has developed rapidly in the last few years to improve hydrodynamic performance. Modifications to the hull configuration and bulbous bow of the catamaran can offer a solution to improve the ship's power by reducing drag. Several studies on the geometric effect of the bulbous bow on catamarans can affect drag and as an anti-slamming, so that it can improve seakeeping performance.
what is the purpose of this study? The purpose of this study is to analyze the geometric effect of bulbous bows concerning drag and the probability of slamming on catamaran.
The primary point of this work is to modify a catamaran NPL bow by adding bulbous bows. The technique involves altering the bulbous bow form by the type and analyzing the hydrodynamic seakeeping factor and the probability of slamming for each shape variation. Catamaran modeling was designed as the initial hull, which is a symmetrical hull with the main dimension is 25.25 meters in length, 2.6 meters in breadth, and 1.4 meters from keel to draft. The ship's overall proportions remain the same, but the bow has been altered to have a bulbous bow. The catamaran types with different bulbous bow shapes are B1.5, B3, B4.5, and B6. Compared to the initial catamaran, B0, the improved from the bulbous bow raised with surface area by 6.3%, 6.7%, 7.8%, and 8.3% respectively. Changes were made to the bulbous bow's length to ship length ratio, but the criteria for breadth and depth remained the same. How to obtain the results by using CFD simulations. Hydrodynamic investigation and the direct component of bulbous bow variation using CFD simulation. Additionally, determining the probability of slamming on the bow and the reaction amplitude caused by movement. Then, let's get to know about ship drag. What does a ship's total drag be made up from? The two parts that make up the total drag are the viscous drag and the wave drag. The viscous drag contains the friction drag and the model's form factor. Then the non-dimensionalized measurement of total drag coefficient, frictional coefficient, and wave coefficient are as follows. This is the process to obtain the ship drag using CFD simulation. First, catamaran models were created in 3D based on the design. Then, following ICCC guidelines, The domain and boundaries of the model were constructed repeatedly. After that, a mixture of prismatic and tetrahedral cells has been subjected to meshing with unstructured parts. In 6 mesh processing runs, various element sizes were used to analyze the convergency number of mesh elements and uncertainties. And finally, the shift drag can be obtained in post-processor section. Another simulation was done to obtain shift response and calculation for the probability of slamming. The ship's global movement generates a response amplitude operator, RAO. The ratio of the amplitude of the ship motions to the wave's amplitude at various frequencies. The RAO describes the ship's reaction to regular waves. Therefore, to get the priceless response, the RAO is squared and multiplied by the wave spectrum. Wave spectrum equations based on the ITCC procedures for seakeeping. The response spectrum value is used to obtain the density of relative motion and relative vertical velocity spectrum, and to calculate the probability of slamming. The probability of slamming can be obtained by this and taking the 1987 Northrop criteria for check of the results. After the simulation, results were obtained, and these are the findings. The result findings on the drag coefficient of the 5 different Bulbous variants. It shows that the modified catamarans have lower values of wave-making drag coefficient. It also shows that catamaran with a more bulbous length has a lower drag. Based on areas obtained from the simulations, areas of relative bow motion were determined. These are areas of relative bow motion, RBM, on variation catamarans bulbous at wave height. This figure shows that the model B6 has the lowest areas of RBM, and model BO has the highest areas of RBM. The response spectra of the relative bow motion according to the mentioned formula were shown in these figures. These are the response spectra of RBM at wave height 0.6 meter, 1.2 meters, and 2.4 meters on the catamaran models BO, B1.5, B3, B4.5, and B6. The results show that the initial catamaran BO has the highest response spectrum for each significant wave height, while model B6 has the lowest spectrum value.
How can it do? The reason is that areas of relative bow motions for the initial model BO are higher than the modified models.
Slamming was simulated to occur at significant wave height and at a threshold speed of 1.4637 meter per second. At a ship speed of 9.44 meter per second, the probability of slamming on catamaran model was calculated as the results shown in this graph. By this graph, we know that as the wave height increases, the probability of slamming increases either. According to the standard seakeeping 1987 Northrop criteria, for fast small craft, the probability of slamming need not exceed 0.03. Catamaran models have a probability of slamming less than 0.03 at a significant wave height of 0.6 meter. However, at wave height of 1.2 meters and 2.4 meters, the probability of slamming is higher than the standard.
This result complies the 1987 Northforce criteria and underreported by another related study.
Finally, we are on the conclusions, and here are what can be concluded. The modified catamaran adding the bulbous wall in geometric variation based the bulbous ball's linear parameters in the drag investigation can minimize wave-making drag more than the initial catamaran. Furthermore, an examination of the probability of slamming showed that at a speed of 9.44 meters per second and a significant wave height of 0.6 meter, catamarans with bulbous balls with the length coefficient decrease the slamming probability comparing the initial catamarans. A check of the Norfolk's seakeeping criteria shows that catamaran can operate safely in the significant wave height of 0.6 meters. However, due to the ship's relatively fast speed, it cannot meet the requirements in the considerable wave height of 1.2 meters and 2.4 meters.
So, this is the end of presentation, and thank you for your attention.